Good morning, everyone. Today, I'm going to present the research that I did at my industrially tied NSF-funded RIPS internship program at IPAM, Institute of Pure and Applied Mathematics, UCLA. This project was undertaken for Google LA. We were a team of 4 undergraduates, Miguel, Sarika, Aviva, and myself. And we were advised by Professor Bao Wang, who is a professor in the math department of UCLA. And our industrial mentors were Vardhan, Akopian, and Schneider. The title of our research is Risk Assessments and Measurements of Privacy Leaks within Google's Ads Data Hub. This is a very high-level view of our poster that I'll be breaking down into smaller segments in the coming slides. Before we proceed to what the problem was, it is worth mentioning what Ads Data Hub or ADH is. Now, Google works with advertising companies to create ad campaigns and place ads appropriately all across the web. They have this system called Ads Data Hub or ADH that stores event level statistics related to the advertisements it posts for its customers. Customers here being advertisers, that is people who use Ads Data Hub. Now, customers, they can generate useful analytics by querying from their system called BigQuery. Now, since this raw information contains sensitive information about users like us, ADH releases aggregated data to protect end user privacy. An example of this is their constraint called k-anonymity, which ensures that any row in the output table contains aggregated information of at least k users. Now, this will make it more difficult to identify individual features of users in the raw table. Now, in addition to these aggregation constraints, it is important to make sure that users' personal information is safe. So our goal for the summer was to develop a framework to quantify the risk of exposing private information in Google's Ads Data Hub. Now, we do this by analyzing the data that the advertisers queried for before the results were aggregated in case an attacker could get through the aggregation constraints. Now, why this project is important is best explained by the Netflix price data set of 2008, where attackers could use benign information such as movie ratings and approximations of when a movie was watched, and they could combine it with external information to reveal sensitive information about people, such as their political affiliations or sexual orientations. I hope this makes understand why research on this topic is important. There was also a Uber privacy leak that happened, and a leak that happened in New York hospital where patients' information was leaked, and a similar situation happened with Netflix dataset. Now to our research. So this is a sample data set that we use to explain our work. To gain familiarity, you can see that there are 5 rows here, or 5 features, that is age, gender, country, language of the people who saw advertisements with campaign ID 1. This is a sample data set that we would just use to explain our algorithm very well. So to solve our problem, we used an algorithm called SUDA, or Special Unique Detection Algorithm. This algorithm, it identifies which attributes make a user more identifiable. That is, for example, if I knew that there exists a person in this sample data set who is from, say, China, then that is enough information for me to identify user number 9 uniquely, right? It is important, I want to reiterate here that we are assuming the worst case. We are assuming that if I am an attacker, for example, and I have found a way through the aggregation constraints, and I can query individual features. So we are essentially working on the raw data set that advertisers query for before the aggregation constraints are applied, right? The next concept that comes here is this sixth row called as minimal sample unique. So what this is this is the minimal number of attribute combinations that can uniquely identify a particular row or user in this case. Um, and this is what we call as minimal sample uniques. For example, if I knew that there is a person in this data set who is a female and who can speak English, and that is enough information for me to identify user number 5 in this database completely. Therefore, gender and language is an MSU for user number 5 in this database. As you can see, for a user, there can be multiple MSU pairs that can exist. As you can see for user number 6, age and country is enough to identify user number 6 in this database, as there is no other user in this data that has a person from 30 to 39 years of age who is from India, and so on. Now after we have calculated these minimal sample uniques for each row in the data set, we need to convert or translate these values into a risk factor that can signify how vulnerable users in this data set are of a privacy leak. We introduce our PIRATE score. PIRATE stands for Probabilistic Identification Risk and Attacker Threat Estimate Score. This is the number of attributes that have to be revealed in order to complete an MSU for a particular row. That is, if I want to identify user number 5, then I would have to reveal gender and language. So to understand this PIRATE score, we are going to imagine the scenario from an attacker's perspective. Let's say I'm the attacker again. And initially, I have no information about the data whatsoever. Now, I start revealing attribute values one by one randomly. Naturally, I will start gaining information about a particular person until their identification, which is when I have caused a privacy leak and breached their system. Now, this will happen with the lowest probability when I have revealed an MSU for the user, as you can see in this table. Let's say for a user, I have 2 MSUs. So let's say I had 7 attributes in the data set, and I have 2 MSU combinations. MSU1 has 3 attributes, and MSU2 and MSUB has 2 attributes, and there are 2 attributes that do not belong to any MSU, right? Now I can reveal an attribute from MSU A with a probability of 3 by 7, and a feature from MSU B with a probability of 2 by 7, and the probability that I will reveal a feature that does not belong to either MSUs is 2 by 7. Now, suppose now I have a very lucky day, and fortunately, I reveal another MSU in, say, MSU set B. The probability of this happening is 1 by 6. But if this happens, then I have revealed MSU B completely. I have uniquely identified this particular user and have successfully breached their system. Now, the probability, now that I have breached their system, then that is it. Like I've caused a privacy leak, and this is what we do not want to happen. So the probability of this happening is this formula that you can see out here, where we multiply these probabilities that we get across each stem, and we multiply it with the depth of the tree. Now what we did, we got sandbox data set from Google. It is important to mention here that the data set that we got from Google does not represent any real data set. That is, it is not the data set of any of their verified advertisers. This is just a sandbox data set that Google created, wherein they randomly sampled values for these particular attributes from a normal distribution. So we conducted different experiments on these on the sandbox data set that we had, and we ran our pseudo algorithm, calculated our pirate scores on these experiments, as you can see. Now, the results of this was, in the first experiment, we took domain, campaign ID, browser, and language information. And this is the column contributions. So in this research, we are also identifying how or what is the contribution of each column or attribute in the data set towards identifying a particular user in the data. So we found that domain and language were highly identifying. This made sense because domains are essentially hyperlinks, which are very varied, and language because since this was a normal distribution, they took languages that have ever existed in human history. That is, it also comprised of languages that do not exist now. So there are a lot of unique languages, which makes it highly identifying. Another set of experiments you can see that we conducted here was using gender, age, country, region, and metro. Country is always 0% identifying because its value was always USA. Region here was relatively more identifying between the second and third example. This was because as we increased the attribute, region could be combined with language and other attributes to identify more users in this data set. Now, on the right side that you can see is the average pirate score on the test sets on different number of attributes that we chose. We could see that as we increased the attributes in general, more users could be identified in the data set. The value for this being low is because in this second trial, we took an absolutely different pair of attributes for our trial. The rightmost column here, the average pirate score, individually it is not as interpretable, but what it signifies is that how at risk the entire data set or how vulnerable the entire data set is of re-identification. As the score increases, as the number of attributes increases, you see the score is also increasing, which makes sense because more attributes, more combinations can exist, which can identify users uniquely. The larger value of this pirate score indicates that this data set that we use in trial number 4 is at more risk, and users here can be identified more easily by an attacker. So in conclusion, we developed a risk measure that quantifies the risk of divulging users' information. Our score tries to evaluate the probability of this breach happening. Our pirate score, as you saw, calculated the expected number of attributes an attacker would have to reveal to completely identify a user in the data set uniquely. The good thing about our score was that it is independent of the size of underlying data set. So we can compare our pirate score across different queries, across different data sets during different time steps. This is significant and matters a lot to the advertisers. Finally, this algorithm is obviously not a perfect execution. For the future work, some suggestions that exist from our side is first mitigation. That is, once we have identified which users are at more risk and which columns are more identifying, we can convert it into mitigation strategies. That is, if we find that a particular user is highly identifying across different tables, then we can probably anonymize the user or remove him or her from the table altogether. Another suggestion here is that attributes are not equally accessible in reality. That is, it is easier for me to identify a gender or age group as compared to a campaign ID. Therefore, we instead of assigning equal weights to the attributes, we can give them we can calculate the weighted average instead of the normal average that we are calculating right now. Also, suppose we identify that age, or suppose we identify that age group is at more risk of identification, then we can probably increase the age bucket. That is, for example, if currently we were calculating age groups in buckets of 5, then if age group is more identifying, we can increase the age group bucket, or vice versa. If it is less identifying, we could also decrease it, and this would make the ADH system more useful for the advertisers. Finally, I would like to extend a huge amount of gratitude to my teammates, Miguel, Sarika, and Aviva, for an awesome research experience and a great summers last year. I would also like to thank Scott Schneider and Vardhan Akopian from the Google A team for cooperating with us and guiding us throughout. I would finally like to thank Susanna Serna, who was our program director, Bao Wang, who was our academic advisor, and the entire team of IPAM for their unconditional support and generosity last summers. Thank you. I will now open the floor for any questions that anybody has, and would happy to address it. If somebody has any questions, I'll be happy to address them right now.
Yeah, thank you. Maybe I have missed something, but have you tested this score on real data already?
So we did not have access to any real data. All we could do was to create our sample data sets and to use the huge amount of data that Google gave us with, which was not a representative of the real data set, because that would be a breach of their contract. Like, advertisers sign contracts with Google, which says that their data cannot be seen by anybody else. So we could not test it on the real data set, but we tested it on the sandbox data set that they gave to us. And we tested it on our sample data sets.
Thank you. And maybe are you planning to make some tests with real data in the future, maybe with some other companies to try to collaborate?
Yeah, so that's an interesting one. So we presented this research at the joint mathematics meeting last year, and we won an outstanding poster in the meeting, in the conference. And one of my friends, Miguel, presented our poster there, and we also had one of the startups that was working in privacy protection, who wanted, to have us on board. We were in talks with them, of running our algorithm on their data, but unfortunately, it didn't really pan out, because all our teammates had different commitments, because we are all in different years and we are all from different places and universities. It didn't really pan out, but I think it would be interesting to run it on a real world data set. We haven't yet gotten a chance to, because the data set in this field, there are so many contracts and there are so many limitations that you cannot have access to a real data set.
Well, I hope that you'll have a chance, because your project is really interesting. Thank you.
Thank you so much. I think we have 7 more minutes. If somebody has any doubts related to the computational capabilities, or if you have any ideas about how, what the next steps or what we can do with it, feel free to throw them here. we can probably brainstorm, or I'll also appreciate any feedback that you have for me.